In this video, we're going to look at a few more examples of constrained optimization to check out the process of Lagrange multipliers, to understand the contour diagrams, as well as think about what does lambda represent. So our first example is not going to be an application problem, but just using this process. So Lagrange multipliers, we want to find the maximum and minimum values of x squared plus 7y, this function of x and y, subject to the constraint x squared minus y squared equals 3. Note that this constraint could be written as g of xy equal to 3. G of xy is x squared minus y squared. So the process of Lagrange multiplier says that we need to find our three equations. We have three unknowns, x, y, and then lambda, and then solve for those unknowns. So we need to find the partial derivatives. So let's do that first. The partial derivative of f with respect to x. We have 7y as constant in terms of x. This is just going to be 2x, the derivative of x squared. And the partial with respect to y is looking at the x squared as constant. This will give us just a 7, the derivative of 7y. Then we also look at the derivatives of g with respect to x. In this case, the minus y squared is constant. So it's just the derivative of x squared, which is 2x. And the derivative of g with respect to y, the x squared is constant. It'll be the derivative of y squared with respect to y, which is negative 2y. Sorry, the derivative of negative y squared, which is negative 2y. Note that the minus 3 or the equals 3 doesn't play a role in here. We just look at the function g when we're doing these derivatives. All right, so our three equations are, the first one is f sub x is equal to lambda g sub x. That's going to give us 2x is equal to lambda times 2x. Next one is f sub y is equal to lambda g sub y. And that's going to give us a 7 is equal to lambda times negative 2y. And the third one is our g equals c, our constraint equation. X squared minus y squared equals 3, the thing that we're given in the problem. All right, so unlike our example in the lecture video, this is going to be a much different process to find x, y, and lambda. And it's good to try to look at these three equations and think about what's the best way that I could eliminate a variable so I can solve for one of these things. And in this problem, it seems like the first equation is really easy to kind of solve for lambda. If we have 2x equals lambda times 2x, you can divide by 2x on both sides, and you get lambda is equal to 1. Right here we have that lambda must be equal to 1 in order for that to be the case. The 2x's just cancel out. Right, that's one of our unknowns solved, and we can use that to find x or y. So now let's look at that second equation. It has just y and lambda, which means that we should be able to solve for y using that lambda equals 1. So here we have 7 is equal to 1 times negative 2y, which means that y is going to be, if we divide by negative 2, negative 7 halves. And then we can plug that into our third equation with the y equals negative 7 halves. We can solve for x. So here we have x squared minus y, which is negative 7 halves, squared equals 3. That's going to be x squared minus 49 fourths equal to 3. If we add 49 fourths to both sides, That's going to give us a 61/4, and we're taking the square root plus or minus the square root of 61/4, which is going to be about plus or minus 3.9. So we've now solved for x, y, and lambda here, and we get 2 points. All right, we get the point positive 3.9 and negative 7/2, and the point negative 3.9, negative 7/2, with lambda equal to 1. And note that we are finding both the maximum and minimum values of this function, and these 2 points are going to correspond to one being the maximum, one going to be the minimum. So let's plug this into the function. Let's see what we get. We have f of 3.9 negative 7/2 is going to be 3.9 squared plus 7 times negative 7/2. So it'll give us a negative 9.25. And note that if we do the negative 3.9 as well, we'd actually get the same answer, because when we square that 3.9 or negative 3.9, we're going to get the same value. So actually here, we only have one of maximum or minimum. We actually don't have the other. So now it's a little bit of a question to figure out, are we finding the maximum here or the minimum? Note that just because this is a negative value does not necessarily mean that this is going to be the minimum. This could be the maximum value that we get is a negative number. So be careful of that trap. We have to do some more work to kind of figure out what's it going to be here. So in order to figure out if this is the max or the min, we have to do some extra work. Note that we can't use something like the second derivative test because we don't have that the derivatives are equal to 0. This isn't a critical point of the function necessarily. This has to do with the constraint. So I think the best way to kind of go about this is just to play around with the functions. In this case, look at any other point on the constraint and see if we get a number bigger or less than negative 9.25. If we get something bigger than it, then we know that that's going to be a minimum. If we get something less than it, it has to be a maximum. So let's just pick x equals 1. Or maybe even better, let's pick x equals 0. That's a nice value to pick. If that's the case, then we have negative y squared equal to 3. And that actually won't work because we can't have a negative with a square root. So x equals 0 is not a good thing to pick. Let's pick x equal 2. That'll be a nice value because we're going to have 2 squared minus y squared equal 3. 4 minus y squared equal 3. You could subtract 3, add y squared. We get 1 equals y squared, so 1 is equal to y. So 1 point on this curve is 2, 1. Just a nice point we pick. We can pick literally any point on that curve. And when we do that, plug it into f. F of 2, 1 is going to be 4 plus 7 times 1 is going to be 11. So this means that since another point gave us a bigger value, then these 2 points represent a minimum. Right? It can't be a maximum because 2, 1 would be another point that would be bigger than that. So those represent a minimum. There is no maximum in this problem. As otherwise we would have that as a point when we do our Lagrange multiplier. Right? And both those points represent a minimum in this problem. And that's okay to have. You can have 2 different points where you get that. All right, so recapping this example, the process of finding x, y, and lambda is much different than we did in the first example in the last video. It's okay to kind of look at all those three equations and figure out, in the first one, we didn't have y. We were able to solve for lambda very quickly. The second one, we didn't have x. We were able to kind of solve for y. And the third one, we don't have lambda, so we were able to solve for x. And there's not just one way you can go about these. There's sometimes an easier way to go about it. But you can just play around with those equations and try to eliminate one variable at a time and go step by step through them. Unfortunately, each question is going to be a little bit different than the last one, so you may have to do different things from problem to problem. Then we plug in those special points that we get, and we saw that we had a value of negative 9.25. We can't just immediately say it's a minimum. We have to do some work to show that it is the minimum, which means finding any other point on that curve, the constraint curve, and show that it's bigger than that negative 9.25. All right, next example has to do with contours. So the figure below shows contours of f of 35, 40, 45, and 50. Those are function values corresponding to different x, y inputs. Let's give an approximate maximum value of f on this graph, so subject to both x and y being in between 0 and 300, subject to the constraint y equals x. And we're going to look at this just graphically, so let's look at what the function y equals x is going to look like. Y equals x is going to go through the points 0, 0, 100, 100, 200, 200, 300, 300. We're going to do a nice line in between all of those. So this is our line y equals x. And what we want to do is we want to find a contour that is tangent to that curve, y equals x. And note that none of the curves that we are given, 35, 40, 45, 50, are tangent to that curve. So our answer is going to be something in between, a contour that's in between. We can kind of see it's going to be somewhere in between 40 and 45. We can maybe graph what it's going to look like. Maybe something like this, kind of following the general shape of the other contours. And there's not a single correct answer, but this might be about 42. It looks like maybe it's a little bit closer to 40 than it is to 45, but it's kind of somewhere in the middle. There's some flexibility in what the right answer could be. All right, so this is kind of approximating that we know it has to be in between 40 and 45, and it looks like it's going to be kind of somewhere in between, halfway in between those two values. This is what I said in the previous video, that the contours, you're going to be tangent to some contour, but that contour may not be something that's drawn in the graph. So you might have to do some extrapolation of the data to kind of see a different contour there. All right, note that the approximate maximum value is 42. That's the maximum value of f on this constraint. All right, we can see the values on that line. None of them are going to be at 45. The 45 line doesn't intersect those. We know it has to be greater than 40 because it intersects 40 twice. Again, 42 is an estimate there. All right, last example, going to an application thing. An automobile manufacturing plant currently employs 1,508 workers and has capital investment of $15 million per month. And we're given production is Q is equal to X to the 0.4, Y to the 0.6, and Q is the number of cars produced per month. We're going to let X be the number of workers, and Y is the capital investment. Each worker's salary is $5,000 per month, and each unit of capital costs $4,000 per month. The question is, how many cars, there's going to be three questions here. First question is, how many cars is the factory currently assembling each month? Well, right now, currently, we have X is equal to 1508, Y is equal to 15 in millions of dollars. So we're going to have Q is equal to 1508 to the 0.4, 15 to the 0.6, plug that in. All right, and I should say, I don't want y to be 15. I'm going to have y be 15,000. All right, this $15 million is going to be the same thing as 15,000 units of $1,000. All right, so we shouldn't have just 15. This is just my fault real quick. We should have 15,000 to the 0.6. All right, this is just the units that we're dealing with. We're not going to plug in 15 million. Our units aren't going to be just $1. It's going to be thousands of dollars. So we have 15,000 thousands. That's 15 million. All right. So when we plug this in, we get a value of about 5,984. 5,984 cars are produced per month at this factory if we have 1508 workers and a capital investment of 15 million, which corresponds to a Y value of 15,000 measured in thousands of dollars. All right, next question. Note that we're just repeating the information on top here. Due to the sluggish economy, the factory decides to decrease production to 2,000 cars per month. The factory wants to minimize the cost of producing these 2,000 cars. How many workers will need to be laid off? By what amount should monthly investment be decreased? All right, and this is our maximizing, minimizing question. We are trying to minimize the cost of producing the 2,000 cars, right? And it's not just minimize cost in general. We have some constraint, and the constraint is we want to have 2,000 cars produced. So let's think about what is our objective function and what is our constraint equation. So the objective function is what we're trying to maximize or minimize. And in this case, that is going to be the cost. So cost is going to be $5,000 per laborer, X, per worker, plus $4,000 per unit of capital, Y. And that's going to be what we're going to try to minimize here. We want to minimize this function. So this is our f of xy here. The constraint equation is our Q, number of cars, which is going to be equal to 2,000 in this case. So note that this seems backwards from the example we did in the lecture video, right? And we shouldn't just assume that it's going to be the same thing problem to problem. We got to look at the problem, see what it says, and go from that information. All right, so we have cost is what we're trying to minimize given the constraint of how many cars we need to produce. And we're just going to try to find out what is X and what is Y. That's going to answer the question, how much need to be laid off, how much should be decreased. All right, so we have to go through our Lagrange multipliers stuff. We have f sub x is going to be the derivative of cost with respect to x. That's going to be 5,000. And that's going to be equal to lambda g sub x. Right, this is our g of xy here. And that's going to be the, let's do those derivatives actually to the side so we can kind of see it. We can actually call this q sub x, which is the same thing as g sub x is going to be the derivative of x, which is going to be bring down that constant, decrease the constant by 1, and then have the constant for y. So putting that in, we have (0.4), x to the negative 0.6, y to the 0.6 times lambda. That's our lambda g sub x. F sub y is going to be 4,000, and that's going to be equal to 0.6 x to the 0.4 y to the negative 0.4 lambda. Doing that work just to show where that comes from. That is, the x is constant, so we're kind of bringing that along for the ride. Bring the power down of y out in front and decrease that power by 1. And then we have our third constraint, which is x to the 0.4, y to the 0.6 is equal to 2,000. All right, so this is a much different kind of problem to solve for x and y and lambda here in these. So we have to think about algebraically how are we going to go about this. So let's do a similar thing we did in the lecture video, and that is let's look at these first two equations and get rid of the lambda in both of them. Right, we can kind of set lambda equal to both sides and then go from there. It's not as easy as it was in the lecture video, but we can still kind of do that. So here we go. Let's look at the first one. We have 5,000 equals 0.4 x to the negative 0.6, y to the 0.6 times lambda. And I'm going to solve for lambda in this equation. So I'm going to divide by 0.4 x to the negative 0.6, y to the 0.6 on both sides. And note that that is going to give me a 5,000 1 over 0.4 is going to be, which is a 2.5, and then 1 over x to the negative 0.6 is x to the positive 0.6. In the same way, we're going to have a y to the negative 0.6. And that's going to be equal to lambda. And we're going to do the same thing for the other equations so that we can set both of those equal to lambda. We can kind of cancel out. I'm not saying this is the only way we can go about it, but this is, I think, the best way, at least that I can see at the moment. So second equation, let's do the same sort of idea. 4,000 is equal to 0.6 x to the 0.4, y to the negative 0.4 times lambda. If we solve for lambda, by dividing by everything else here, we get lambda is equal to 4,000. We have 1 over 0.6, which is 1 over 3/5. That's 5/3. We'll just write that as 5/3 right now. X to the negative 0.4, y to the positive 0.4. And now we have the equation of, we can set these two equal to each other to solve for x and y. We've eliminated the variable lambda. All right, I'm going to do that on the on another page here. So I'll come back to this to reference it in a little bit, but let me go find a blank page real quick. All right, so we have 5,000 times 2.5 Let me make sure I have these values correct. X to the 0.6, y to the negative 0.6 is going to be equal to 4,000 times 5/3 x to the negative 0.4, y to the 0.4. The reason we could do this is we had lambda equal to both of these, so we can set them equal to each other. Right, so now we have a bunch of different constants floating around, but we can multiply both sides here by x to the 0.4 that's going to get rid of these two terms. As you add the exponents, you'll get x to the 0, which is just 1. And here we'll have just x. And we can do the same thing for the y's as well. We can multiply by y to the 0.6. Which will get rid of these terms, and we'll have a equal to y on this side. And then we just have the constants floating around. That's going to give us our answer. So 5,000 and 2.5. Okay, those constants will be a 12,500. And the other side we have 6,666.67. And 2/3 is what we have there. Just using decimals is fine right here. So we could write that maybe x is equal to 0.533y, about. All right. Now we're going to use the other equation there, the fact that x to the 0.4, y to the 0.6 was equal to 2,000 to solve for x and y here. So here we have that 0.533y to the 0.4, y to the 0.6 would be equal to 2,000. That's plugging in x is equal to 0.533y. And this will give us a 0.533 to the 0.4, y to the 0.4, y to the 0.6 equals 2,000. Note that that's just going to be equal to y equals 2,000. So we could say that y is going to be equal to 2,000 divided by whatever this value is, 0.533 to the 0.4. Plug it into a calculator and we get about, right, this is about 2572.4, which means that x is going to be 0.533 times whatever that y value is, which is about 1371. All right, so now let's go back to the original question. We have 2572.4, 1371. Let's actually answer the question now. All right, how many workers will need to be laid off? Well, we know now that x equals 1371 is how we're going to minimize cost. So we should have 1508, what we started with, minus 1371, which is 137 workers should be laid off. And by what amount should the monthly investment be decreased? Well, we found that y is equal to 2572.4. This was measured in thousands of dollars. So we take that and multiply it by 1,000. We get 2572,400. Sorry, one more. Nope, they're right there. That's 2 million about. So we should be decreasing 15 minus $2.572 million, which will be about a decrease of $12.428 million. That's actually answering the question. Again, that's just using our x and y values that we found to answer the question there. All right, last question for this problem. Give the value of the Lagrange multiplier lambda and interpret it in terms of the car factory. So let's use just one of our equations here that we found. Let's use that guy right there. It already has lambda equals. And we're going to plug in our values of x and y into that problem. So we have, this was a 12,500 x to the 0.6, y to the negative 0.6 equals lambda. And we had that x is equal to, checking the values, 1371 and y was 2572.4. 1371, y was 2572.4 about. So plugging this in, we're going to get a value of, which is about 8,569. So what this represents in terms of the car factory is that if we increase the amount of cars that we produce, if we increase the amount of cars produced by 1, the cost will increase by $8,569, or the cost to produce a car is $8,569. So this value of lambda is very important and very useful in that now you know the cost to produce a car, so you can think about, well, what if we wanted to do 2,500 cars instead? That's a very easy calculation to kind of determine how much that's going to be, how much the cost is going to be.